Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle force, episode 11, seminar 2, in which we will solve our next problem, number 12, in which we're asked to construct all circles that are tangent to two given coplanar circles, Q1 and Q2, and that pass through a given fixed coplanar point P that is located strictly outside of both of the given circles Q1 and Q2. All the solutions to this problem can be roughly partitioned into two distinct piles. Into one pile, there go the solutions of this problem that are based on elementary mathematics, and into the second pile go all the solutions of this problem that are based on mathematics that is less elementary or not elementary, depending on the stance that you take towards the objects known as cyclides of Dupin. And one such cyclid, in particular a ring cyclid, can look as follows. And the way the history went in real time, these objects, to which we now refer as cyclides of Dupin, were invented by an 18-year-old French gentleman whose last name was Dupin, and he lived between the years of 1784 and 1873. These ideas apparently boiled and simmered in his mind for about 1 year, and when he was 19 years old, he defended his dissertation in the year of 1803. And when that happens, then all the entire body of mathematics that is included in the dissertation enters the bigger texture or the greater landscape of official mathematics. And these days we know that the cyclides of Dupin come in different varieties. They could be ring cyclides, they could be spindle cyclides, and they could be horn cyclides, depending on the specific geometric ingredients that go into the creation of these cyclides. As such, this particular problem, the problem number 12, or the problem of constructing all circles that are tangent to two given coplanar circles, and the ones that pass through the given fixed point P that is located strictly outside of these given circles, is based precisely on the machinery afforded by cyclides of Dupin. And that solution actually plows through the process of construction of so-called cones of revolution, spheres, and planes. And at a certain point in this particular solution, the arrangement of cones of revolutions and spheres is cut with the plane, and in that cut plane we obtain a two-dimensional setting that is embedded into the parent three-dimensional setting, and that two-dimensional setting offers precisely the blueprint of the solution of this problem. And due to the mechanics of how the cyclides of Dupin work, we now know that this specific problem has four real solutions and four imaginary solutions. And depending on your level of mathematical maturity, the moment you hear the word imaginary, then your favorite imaginary unit, which we usually designate with the lowercase letter I, which can also be a generator of the finite commutative multiplicative group of fourth roots of unity, comes to mind. But precisely because the name of this course is inversion of the real plane with respect to a circle, we will ignore all the solutions of this problem that are imaginary, and we will concentrate on the solutions of this problem that are real, of which there are four. Moreover, all the solutions of this problem that are based on elementary mathematics can also be roughly partitioned into two distinct piles as far as our course is concerned. These elementary mathematics solutions do involve the machinery of inversive geometry, and The other such solutions do not involve the machinery of inversive geometry. We recommend that you try to solve this problem without using the machinery of inversive geometry, and as a hint, one such solution is based on the following idea. All the circles are actually similar, and that means that with this help of the geometric transformation known as the homothency of the parent plane, with the center of homothency picked appropriately, the larger circle can be uniformly compressed into the smaller one, and conversely, the smaller circle can be uniformly expanded into the larger one. And in their most general position, as the one shown on the right side of your screen, such two circles will always have two distinct centers of similitude, or two distinct centers of homothency under the homothency of the plane with respect to which the circles will be uniformly taken one into another. Of course, you remember that as a geometric transformation, homothency is precisely that, a uniform expansion or contraction of the parent plane with respect to a specific point. In this case, our two circles will have two distinct centers of similitude, or two distinct centers of homothency in this most general position, especially when the radii of the given circles are different. In this particular case, there will be one center of similitude that is called external. It will be located always on the side that is pointed to in a way by the circle of the smaller radius. So in this case, the external center of similitude will be located behind the board on the other side, and the internal center of similitude, or the internal center of homothency, will be located precisely on a straight line that connects the centers of these two circles, or the line of centers, and strictly in between the centers of the given circles. Now, once the locations of these centers of similitude are known, it is possible to construct in the general position four distinct tangents, two external and two internal, and then take this idea all the way home to victory and construct the circles that are required in this case. And as another hint, with this idea that all the circles are similar, it is also possible to reduce this problem that deals with circle point to a slightly simpler problem in which we have only one circle and two distinct points. Either way, we highly recommend that you try to solve this problem both ways, using the elementary mathematics that does not involve the machinery of inversive geometry, and in another way, which does involve the machinery of inversive geometry, and then compare the textures of the two. And when you will do so, you will discover that the solution of this problem that is based on the machinery of inversive geometry that we're about to discuss is actually way simpler, because the other solution type, the one that is based on the idea that all circles are similar, requires quite a bit or non-trivial amount of creativity and ingenuity. And without further ado, let us see how this problem can be solved using precisely the machinery of inversive geometry that we have studied so far. We will solve the current problem number 12, as we will do pretty much all the problems in this course, using the combination of two problem-solving approaches, the so-called transform and conquer problem-solving approach, and the reverse order or the reverse time flow problem-solving approach, which we studied in a dedicated manner on this channel in the following episodes. We studied the transform and conquer problem-solving approach across the episodes in Season 1, Episode 3 through Season 1, Episode 7, inclusive in all cases. This makes up for a total of 5 episodes, and all these 5 episodes live in its own playlist that is cleverly disguised under the name Transform and Conquer. All the problems that we solved when we were studying the reverse order problem solving approach were covered in Season 2, Episode 3 through Season 2, Episode 10, inclusive in both cases, for a total of 8 episodes, and all these episodes are put together into its own dedicated playlist that is cleverly disguised under the name of reverse order. You can either search this channel directly if you're good at manipulating this platform on your own, or you can use the Season 1 and Season 2 guides. These are the free PDF files that are compiled for every season on this channel. The links to these files are in the comment section to this episode, so in the matter of 2 or 3 clicks, you can get to this episode, study this material, because if you do not know this material, if you are not familiar with it, you will be completely lost, and I will assume that you know this material at least as well as I do, and hopefully even better. As such, we will use the reverse order problem solving approach in order to solve the problem number 12 by assuming first that this problem has been solved somehow. We do not know how yet, and in some sense we do not care. But the reason we make this assumption is because we want to analyze the problem in the solved state in order to glean certain useful, tactically useful insights into the given problem, so that we can generate the requested or the traditional forward flow of causality order solution. And when we do that, what do we see? Let us say that somehow one solution circle shown in red is constructed, and that solution circle passes precisely through the given fixed point P and 2 given coplanar circles that are shown on top, not these circles but these circles, not hatched. And what can we do next? Well, next we want to bring in the so-called transform and conquer problem solving approach in general, and the adjustment of the transform and conquer problem solving approach specifically to the inversive geometry setting was already done by me in the previous episode. If you missed the previous episode, it is a good idea for you to watch that episode as well, because if you do not understand how the reverse order problem solving approach works, if you do not understand how the transform and conquer problem solving approach works in general, and how it works when adjusted specifically for inversive geometry, then you will be totally lost and you will completely miss the point and not understand how and why we will be able to solve this problem in about 30 seconds or less. Meanwhile, following the heuristic template that I described in the previous episode, we now think we want to fix or find a fruitful center of inversion, radius of inversion, power of inversion, and the number of inversions or a composition of inversions, and see if we can solve the inverted problem, because precisely this is the idea of the transform and conquer problem solving approach. Gain a competitive advantage in a transformed setting where the original difficult to solve problem becomes more tractable and more easier in some sense to solve. To that end, putting the reverse order problem solving approach aside for a second, we now bring in the specifically adjusted for inversive geometry transform and conquer problem solving approach and think, what do we know about circles that pass through interesting points? Well, we know that any circle that passes through the center of inversion is taken into a straight line under the corresponding inversion of the real plane with respect to a circle with both powers, positive or negative, and regardless of the specific mutual juxtaposition of that circle and the circle of inversion. And in this case, we see that if we bestow an honorary title on the given point P to be the center of inversion, then our solution circle, such as the red solution circle over here, will be taken by the inversion of the corresponding plane with respect to a circle C that has precisely the point P as its center and any arbitrary radius of inversion will be taken into a straight line, and the straight lines in this context we usually treat as objects that are easier to deal with, because when it comes to tangency, we know how to construct tangent straight lines to circles, and we do not know yet how to construct tangent circles to, for example, two given circles, and the proof of this statement is precisely this problem number 12. As such, in this analysis, what do we see? If we invert the solution circle shown in red into a straight line, then that inversion with positive power with respect to a circle of inversion that has precisely the point P as the center and any arbitrary radius will do also what? Not only it will take our solution circle into a straight line, but it will take our original circles shown on the left and shown on the right precisely into genuine circles. Why? Precisely because, as we proved in the previous lectures, if a circle does not pass through the center of inversion, which in our case it does not. Why not? Well, remember the requirement that we had imposed on us by the statement of this problem. The point P is located strictly outside of the given circles. That means that our original circles will be taken into genuine circles, and we will have the situation where the image circles will afford the solution of the problem in terms of the inverted objects, because we know how to construct a tangent straight line to these image circles. This is precisely where we gain the tactical advantage or the competitive advantage, because we take the problem of constructing a tangent straight line to two given circles as a previously solved problem. We solved that problem on this channel in Season 2, Episode 6, under the guise of the mathematics problem S2M9. If you do not know how to solve this problem, then you can either try to solve the problem on your own and then realize that this is precisely where we gain the competitive advantage, or you can watch our presentation here. We show actually several ways to construct these tangents. In most general case, there will be 4 such tangents, 2 external and 2 internal. But here, as an official declaration of victory, we recall also the theorem number 37 that we proved in the previous lecture. And in that theorem, we proved that the tangency points are preserved under any inversion of the real plane with respect to a circle under both positive and negative power. As such, in this case, we see that the solution of the inverted problem, or the solution of the problem in terms of the inverted objects, is either easier in some sense, or it is a previously solved problem. This is where we gain the competitive advantage. And according to the theorem 37, if, let's say, temporarily our original objects touch each other at 2 distinct points, for example, this straight line touches this circle at a certain point, and the same straight line touches this circle at this point, then according to the theorem number 37, under the corresponding inversion, these objects, these 3 objects, will also touch each other when inverted in the same circle with the same power, for as long as, again, remember, the stipulation of the theorem number 37 was that the tangency points are distinct from the center of inversion, and they are in this case. So now, again, at the bird's eye view, here is the idea of the solution of this problem. We pick the point P, the given fixed point that lies strictly outside of the given circles Q1 and Q2, as the center of inversion. We pick the power of inversion to be positive. That is enough. The radius of inversion in this case does not matter, and I will come back to that idea in a few minutes later at the end of this episode. But using these parameters of inversion, the center of inversion, the radius of inversion, the power of inversion, and the number of inversions. In this case, 1 is enough. We invert our original circles into genuine circles. Then we solve the inverted problem by constructing 4, in most general case, tangent straight lines to the images of our circles under the chosen inversion. And as I explained in the heuristic template in the previous episode, at this stage, we need to convert the solution of the problem in terms of the inverted objects into a solution of the problem in terms of the original objects. And how do we do that? Well, in this case, we simply flip our tangent straight line that has only one point in common with each circle, with each image circle in the same circle with the same power, back into what? Into a solution circle. And the game is over, and we can write down an efficient algorithm that solves this problem using the Euclidean tools alone. Remember that first and foremost, especially during your formative years, mathematics is an art of telling a story. Mathematics is an art of telling a story of how and why, which means that for you right now, the most important thing is to develop the ability to tell that story, because if you're telling a story, then chances are that you will solve the problem. And conversely, if you are not telling a story, then you pretty much will not be able to solve a problem. In this particular case, we told a story of how a solution of this problem can be generated, and once we convert that story into a sequence of potentially dry steps and we present these steps to the bewildered audience, that audience will be completely amazed. How on earth did he or she come up with these steps? Where did they come from? Well, we know where did they come from. We told the story. The reverse order problem solving approach, the transform and conquer problem solving approach, adjusted for the inversive geometry, and this machinery pops out the following wonderful algorithm that solves the given problem with Euclidean tools alone, as requested, with absolute certainty and correctly. Again, we consider the most general, the most interesting case when all the points are finite and we have the maximum number of real solutions. First, we invert the given circles Q1 and 2 into the genuine image circles Q prime 1, 2 in an arbitrary circle C that has the point P as the center of inversion and any strictly positive real number as its radius, as long as this radius is greater than 0. Again, in a few seconds, I will show you what does it mean that in this particular case, the radius of inversion does not matter. We do this inversion, we carry out this inversion of the parent plane with positive power. Once is enough, no fancy compositions, no change of inversions. And here I'll show you the circle Q1 is the first such circle, the circle Q2 is the second such circle, P is the center of inversion, the circle shown in white, this circle right here, let's pretend this is the circle of inversion lowercase c. Its radius does not, the magnitude of the length of the radius of inversion in this case does not matter, but remember the average rule of thumb, if you will, that we want to pick the for the magnitude of the length of the radius of inversion, we want to pick such a value that minimizes the amount of non-trivial work that we have to do non-trivial inversions. Once we have the image circles Q prime 1 and Q prime 2 on the books, these two circles over here, they're hatched so that you can distinguish the image circles from the original ones. That's it, game over. The step number 2, we construct, for in the most general case, tangent straight lines to external to internal, which we call the straight lines T for tangents 1, 2, 3, 4. In the most general case, there will be 4 such straight lines to the image circles Q prime 1, 2. And precisely again, this is the point, this is the step where we gain the competitive advantage, because in the transform setting, the problem became much more tractable and much more easier in some sense. We know how to solve this problem. And as the last step, the third step of our algorithm, we invert the constructed in the previous step tangent straight lines T1, 2, 3, 4 into the four solution circles, which we name W1, 2, 3, 4. On the board on the left side, I know that it looks like an impenetrable jumble of mess, but here it is important to realize the following thing. I personally solved a fair amount of problems using the inversive geometry. I have a fairly good understanding and feel for how these things work. And it is one thing for you to look at the board and comprehend analytically the steps that we take. This is fine, but in order to deepen your personal level of mathematical maturity, in order to deepen your understanding of the material, and in order to develop your predictive powers, I highly recommend that you shadow and that you trace all these steps that I show on the board with your favorite graphing software on your own. It is very important to act and do these things on your own, because only through your personal effort will you be able to increase your level of mathematical maturity, understanding of the material, and your predictive powers. Do it with your own hands. Do experience all this. And the good news here is that you do not need any fancy graphing software at all. I use, for example, the free software called GeoGebra, and just about the only technical functionality that you need in your software is the basics of Euclidean geometry. You need to be able to draw straight lines, and then you need to be able to draw circles, and in some sense, this is it. All this work that you see on the board over here can be done with just these two functionalities, using the main ideas and the main apparatus of Euclidean geometry. With the straight edge and a circle alone, we can draw parallel lines, perpendicular lines, and on and on and on. And all the material that we covered so far proves that all these steps can be carried out with Euclidean tools alone. And when you will be doing all that work using your favorite graphing software, you will be, like I said before, developing your powers of mathematical prediction, saying these words. Let's say concentrate. We will call this external tangent, as I named as T1 over here, and we will think, where will this tangent straight line T1 be taken when inverted in the circle C that has the center P with the positive power of inversion once? Well, we know that the tangency points must be what? Not only they must be preserved, but they must be what? They must be collinear with the center of inversion, P. In other words, we take our center of inversion, P, we take our first point of tangency, we know that this straight line must contain the image point, and we know that this straight line T will be taken into the circle, which I call W1. In this case, the circle W1 will touch both of the given circles internally, because the circle Q1 and Q2, the given two circles, will be located strictly inside of the first, let's say, solution circle W1. And when cleaned up and done professionally, like I did with the free software called GeoGebra, that particular construction step will look as follows. Next, you will take the second external tangent straight line, the one that I called T2. Let's pretend that this is the straight line. This is the straight line that we worked with in the previous segment. But let's say we refer to this tangent, external tangent, and T2, and we say, where will this tangent, that is, represents a solution of the inverted problem, be taken into? Again, inversion preserves the tangency points, and these tangency points have their images. These images are unique, and they must be what? They must be collinear with the center of inversion. As such, in our mind's eye, we draw this straight line, we draw this straight line, we see, this straight line, this tangency point will be taken into this point, this tangency point will be taken into this point. Our straight line T2 that is tangent to the image circles Q prime 1, Q prime 2 will be taken into the circle W2 that in this case, this guy right here touches both of the original circles. Which way? Touches both of these circles externally, and when cleaned up, done with the professional software such as GeoGebra, for example, that step of the construction will look as follows. Next, you will move on to the tangent number 3. Let's find it on my drawing. Again, I apologize for it being a total royal mess, but because I work by hand, this is so, but we still have our power of analytic thinking, and let's say this is our tangent T3. This time, this tangent is called internal. It passes precisely through the internal center of homothety of these two circles. And again, we know that according to the theorem number 37, the tangency points under any inversion of the real plane with respect to a circle with both powers are conserved, and the images of these points must be unique. This is another theorem that we proved early on in our course. Geometrically, these points must be collinear with the center of inversion. So we grab our internal tangent named T3. This tangent runs this way. Maybe if I show you guys this way, it will be more helpful. It is this straight line right here. This tangent will intersect, let's say, the circle of inversion at 2 points. Remember the mechanics of constructing such solution or inverted images of the straight line. So our internal tangent T3, this one, will be taken into a circle that I call W3. This circle will run this way through the point, through the intersection point, through the common point. Recall all our theorems and beautiful problems that we solved using the Euclidean tools alone. This circle is shown over here partially, closer to your left side of the screen. But what do we see in this case? In this case, we see that this solution circle number 3 will touch the original circle Q1 internally while touching the other circle Q2 externally. When cleaned up, that step of the construction will look as follows. Finally, we move on to the tangent number 4. That will be also an external tangent. It is shown over here partially. This is the tangent T4. I designated it here as T4, if you can see that. The two internal tangents T3 and T4 intersect at the internal center of homothety. In this case, the homothety will be taken out, carried out with negative power, and then the smaller circle can be taken into the larger one and larger into the smaller one. But developing our powers of mathematical prediction, we think, where will the tangent, the internal tangent T4 be taken to? What will be its image under the chosen parameters of inversion? Well, that tangent will intersect our circle of inversion, let's say, at this here point and this here point. And we remember that according to the appropriate theorems that we developed early in our course, our inverted image of that straight line will pass precisely through these 2 points and the center of inversion, which is overloaded to carry the function of the given fixed point P. And we see that this straight line will be taken into this circle, shown only partially. The circle number 4 will run this way. I named it the circle W4. And in this case, what characteristic property of this circle do we see? In this case, we see that the circle touches the first, or let's say the circle Q1 externally, but it touches the other circle Q2 internally. And just in order to make sure and make it explicit, you see that I paired up the tangent straight lines with the solution circles based on the index. In other words, the index T1 for the tangent straight line named T1 corresponds to the solution circle W1. The tangent T to the tangent straight line T2 corresponds to the second solution circle W2, and so on, T3 to W3, T4 to W4, so that you can see the straight line T1 is taken into the circle W1, the straight line T2 is taken into the circle W2, T3, W3, T4, W4, four solution circles. Now, once you inhale all these solutions, what characteristic property of this solution do you see? An observation that you were expected to make on your own is the following. In the most general, of course, and in the most favorable case, the solution of the problem 12 will consist of a family or of a set of four solution circles that has the following property. Precisely one solution circle will touch both of the given circles externally. And in our case, that was the solution circle number 2. It touched both of the given circles Q1, 2 externally. In the family of solution circles, precisely one circle will touch the given circles internally. And in our case, that was the solution circle W1. It enveloped the given circles Q1 and Q2. Moreover, precisely one solution circle from the family of solutions will touch one circle, such as Q1, externally, while touching the other circle, such as Q2, internally. That was the circle number 4 in our case, W4. This circle right here, remember that it touched the circle Q1 externally while touching the circle Q2 internally, and vice versa. Precisely one circle in that family of solution circles will touch the one circle internally, such as the circle Q1, while touching the other circle, the remaining circle, such as Q2, externally. And in our case, that was the circle number 3, W3, this circle right here. It touched the circle Q1 internally while touching the circle Q2 externally. Now, this is almost it for the problem number 12, and here I would like to take an opportunity to come back to the observation that I made in the very first lecture, where I defined the geometric transformation of inversion of the real plane with respect to a circle. And back in that lecture, I observed that in general, not of course always, but in general, the magnitude of the length of the radius of inversion, the specific one, does not really matter. As such, on average, or as a rule of thumb, we like to pick the exact length of the radius of inversion in such a way so as to minimize the amount of non-trivial work, which means that we would like to pick the length of the radius of inversion in such a way that the number of objects that are not taken into itself by that inversion is as small as possible. However, in most cases, like I said, since the length of the radius of inversion is irrelevant, what does that actually mean? Can we see the physical manifestation of this idea? And here right now in this course, we came exactly to that juncture point where we can see what does it mean when we say that the exact length of the radius of inversion is irrelevant. In order to bring this idea to you in as visual fashion as possible, I put together not exactly an animation, but an animated demonstration using the free software called GeoGebra. And in that animation that you are about to see in a few seconds, you will see the following. It will be, honestly, it will be a very complicated and a very involved animated demonstration because there will be a lot of moving parts, but I would like you to pay attention to the following. In a few seconds, you will see a point that sits precisely on a blue circle of inversion that I made visible because I have to drag it, and that's pretty much the only convenient way in GeoGebra to control the parameters of a particular geometric object on which it is built. So you will see one point that sits precisely on the circle of inversion. That circle of inversion will be at the bottom of your screen. It will be shown partially. We technically even do not really need that. But do not pay attention to that point because I will use my mouse and I will wiggle that point in order to play with the radius of inversion, and this radius will diminish and it will increase. I will wiggle that radius back and forth. As I do that, you will see that the position and the size of the blue tinted or shaded in blue image circles will also change. The size and the position of the image circles will change. Along with the change in the size and the position of the image circles, the corresponding tangent straight lines, the external and the internal tangents, will also change their position, but I will not reveal more than I have to. The tangents in this case will change their position in a specific way. See if you can catch what is going on over here. And as such, you will see that in this animated demonstration, how many objects will change. The circle of inversion will change. The position and the size of the two image circles will change. And the positions of the four tangent straight lines will change. However, do pay attention and see what is going on with the four solution circles. What exactly do you see? I hope that everyone in the audience noticed the following interesting phenomenon. As all sorts of auxiliary constructive material breathed and lived its own life, danced around in some elaborate dance, our solution circles, actually none of the solution circles, none of the four solution circles moved a muscle. In other words, all four solution circles, W1, W2, W3, and W4, remained where they were as all the intermediate constructive material danced its elaborate dance. And this is precisely a visual demonstration of the fact that the exact length of the radius of inversion in this particular case does not matter. And as an informal homework assignment, I recommend that you try to think on your own and try to figure out on your own why that is. Meanwhile, this is it for the problem number 12. This is it for the seminar number 2. And I will see you in the next seminar where, as a fair heads up and as a fair warning, we will solve a slightly more elaborate problem in which we will be given 3 circles which are coplanar and which intersect at one point. Let's say again, we'll call that point P, and the task and the objective in that slightly more elaborate, more difficult problem will be again to construct all circles that are tangent to such 3 circles.